This is Unit 2, Lesson 2. Estimate the instantaneous rate of change of a function at a single point. In our last lesson, 2.1, we calculated the average rate of change of a function in an interval. So for example, an interval might be from x equals 3 to x equals 5. That's an interval. So if we have a graph, here's our graph. An interval might be, say, from here to here. From here to here, that's an interval. In this lesson, we will find the instantaneous rate of change at a single point. So say, for example, from at x equals 4. So we're not looking for one region. We're looking at a point maybe right here, this point. We want to find the slope at this point. Okay. All right. So what's the difference between average and instantaneous? For example, if a car has traveled a distance of 3 meters after 2 seconds and a distance of 9 meters after 4 seconds, we can find the average speed during that interval from 2 seconds to 4 seconds. To find the average speed, that's like the last lesson. The distance, well, the speed is going to be the change in distance over change in time. The change in distance, well, we're going from 3 to 9. So 9 meters minus 3 meters. The time, we're going from 2 seconds to 4 seconds. 4 seconds minus 2 seconds. That's 6 meters over 2 seconds. That's 3 meters per second. So the average speed is 3 meters per second. Instantaneous speed is different. To figure out the instantaneous speed, we want to know exactly how fast the car is going at t equals 3. Because maybe it's speeding up, maybe it's slowing down. To figure that out, we have to look at a speedometer of the car. It will tell us how fast it's going, like 10, 20 miles per hour, 30 miles per hour, and so forth. Okay, so let's look at an example. Again, from last time, slope is the rate of change. We have our average rate of change. We can use this formula to help us find the instantaneous rate of change at a single point. We can estimate it using average rate of change. Our example, here's our function. F of x is 0.5x to the third power. We want to find the slope, the instantaneous slope at x equals 2. Let's type this graph in. So here's our graph, 0.5x cubed. We want to know how quickly this graph is moving. So for example, right here, at around 0, 0, the slope is very small because it's not going up very quickly. But here the slope increases because it's getting steeper and steeper and steeper. So the slope is increasing. We know the slope is increasing, but exactly how fast it's going up. What is the slope at this point? X equals 2, f of x equals 4. Well, to do that, we can estimate. For example, we can estimate, we can estimate using the interval 1 to 3. I'm going to have to zoom out a little bit to see that. So let's zoom out. Okay. To estimate the slope from 1 to 3, we have to go from here all the way to here. That will give us the slope of that line. Well, let's figure that out. It's not easy to estimate from the graph. Let's calculate it algebraically. So when the interval is x equals 1 to x equals 3, the average rate of change from last time is f of 3 minus f of 1 over 3 minus 1. So let's figure out what x is 3 is and what x is 1 is. We can go here. When x is 3, f of x is 13.5. So that's 13.5. When x is 1 is 0.5. So minus 0.5. That makes sense. because 1 squared is 1 times 0.5 is 0.5 over 3 minus 1, which is 13 over 2, which is 6.5. So the estimate, if we use the interval 1 to 3, is 6.5. This estimate is not that great, as we saw on our graph. We're going really far from here to here. A better estimate is if we come closer. What if we use 1.5 and 2.5? Like here to here. Okay. So let's calculate that algebraically. That's f of 2.5 minus f of 1.5 over 2.5 minus 1.5. So go back to our scientific calculator. When x is 2.5, f of x is 7.8125. Okay. 7.8125. And when x is 1.5, let's plug it in. F of 1.5 is 1.6875. Divide by 2.5 minus 1.5. So we have 7.8125 minus 1.6875. When we subtract this, we get 6.125 divided by 1, so 6.125. So we see that when we get closer, instead of using x equals 1 to x equals 3, we use x equals 1.5 to x equals 2.5, and the slope is about 6.125. That makes sense. Earlier, we're overestimating the slope, and now we're getting closer. To get even closer, we can do f of 2.1 minus f of 1.9 over 2.1 minus 1.9. If we do the calculations, f of 2.1 is 4.6305. 4.6305. And f of 1.9 cubed divided by 2 is 3.4295. Let's plug in 3.4295. Divide by 2.1 minus 1.9. Let's subtract using a calculator. 4.6305 minus 3.4295 gives us 1.201. 1.201. 1.20. Okay. 1.201. 2.1 minus 1.9 is 0.2. 1.201 divided by 0.2 is basically 1.2 times 5, because divide by 0.2 is the same as multiplying by 5. So it has to be 6.005. So we see that it's getting closer to 6. That would be my guess for the slope, actual slope. Let's get even closer. This time we use 2.01 and 1.99. So when we plug in 2.01, f of 2.101 is 4.0603005. Type that in here. 4.0603005 minus f of 1.99. That's 3.94. 02995. Write that down. 3.94. 02995 over 2.01 minus 1.99. When we do the subtraction, we get 0.12 0.0001 over 0.02. Calculate that, and we get 6.00005. So we're getting, see that the slope is getting closer and closer to 6. Let's summarize our results in this table. When we use x equals 1 to x equals 3, we see that we get the answer 6.5 for the slope. When we get closer, x equals 1.5 to x equals 2.5, we get 6.125 as the slope. Then we got 6.005 as the slope. Then we got 6.00005 as the slope. As we can see, the slope is getting closer and closer to 6. So we can estimate that the instantaneous rate of change of f of x at x equals 2 has to be probably around 6. It's still a guess. We haven't proven that this is true, but this is getting closer and closer to 6. 6.5, 6.125, 6.005, 6.00005. We can say that the limit of this sequence of numbers seems to be 6, going back to unit 1. So to summarize, what did we find? We have the function f of x equals 0.5x cubed. It seems that the slope at this point seems to be at roughly about 6. And that's it for this video.